In an earlier video, we introduced the idea of an equilibrium point. An equilibrium point is a value or set of values where the system can remain unchanged. In this video, we focus on how to actually find equilibrium points in nonlinear ODEs. The basic idea is simple. At equilibrium, the system is not changing, so the time derivatives are zero. Once we set the derivatives to zero, the differential equation becomes an algebraic equation. Finding the equilibrium points then means solving that algebraic equation. In that sense, it is similar to finding roots. But these are roots of the equilibrium equation, not characteristic roots of a linear ODE. Let's turn this idea into a general procedure. We write the ODE as one expression equal to zero and call that expression f. For example, f might depend on x, x dot, x double dot, and the input u. At equilibrium, the system variable has a constant value, which we write as x sub e. If there is an input, the corresponding equilibrium input is also constant, and we write it as u sub e. Because the system is not changing at equilibrium, the time derivatives are zero. So, x dot equals 0 and x double dot equals 0. Substituting these equilibrium values into f gives f of xe 0, 0 ue equals 0. This is the equilibrium equation. It is no longer a differential equation. It is an algebraic equation. Depending on the problem, we might be given ue and solve for xe, or choose xe and solve for the corresponding ue. Sometimes we might simply check whether a proposed value or pair is actually an equilibrium. We first look at a simple nonlinear example. Suppose we have the first order ODE x dot equals x cubed minus x. This equation is nonlinear because of the x cubed term. Equilibrium occurs when x dot equals 0. So the equilibrium equation is xe cubed minus xe equals 0. We can factor out xe, giving xe times the quantity xe squared minus 1 equals 0. This gives three equilibrium points. xe equals minus 1, 0, and 1. The graph shows the same result visually. The equilibrium points are the places where x dot is 0, so they appear as the x-axis crossings of the curve x dot equals x cubed minus x. The main point is that nonlinear ODEs can have more than one equilibrium point. A simple first-order linear equation usually has at most one equilibrium point. Nonlinear equations can have several because the curve can bend and cross zero multiple times. Here, finding the equilibrium points was essentially the same as finding the roots of the algebraic expression x cubed minus x. But these are roots of the equilibrium equation, not characteristic roots. Now, let's look at an example where an equilibrium point may or may not exist. Suppose we have the first order ODE x dot equals e to the x minus a, where a is a constant. This equation is nonlinear because x appears inside the exponential function. Equilibrium occurs when x dot equals 0. So the equilibrium equation is e to the xe minus a equals 0. Rearranging gives e to the xe equals a. To solve for xe, we take the natural logarithm, giving xe equals ln of a. But this only makes sense if a is positive, because e to the x is always positive. So if a is greater than 0, there is one equilibrium point. If a is less than or equals 0, there is no finite equilibrium point. The graph shows the same idea visually. When a is positive, the curve e to the x minus a crosses the horizontal axis once. But when a is 0 or negative, the curve does not cross the horizontal axis, so there is no equilibrium point. The takeaway is that solving the equation is not always enough. We also need to check whether the solution actually exists for the values allowed by the nonlinear function. Let's now return to the example x double dot plus cx dot plus k sine of x equals u. This is the nonlinear ODE that we previously linearized near a chosen equilibrium. In that discussion, we mostly assumed that an equilibrium had already been chosen. Here, we look more carefully at how to find those equilibria. At equilibrium, the system is not changing, so x dot and x double dot equals 0. We write the equilibrium position as xe and the corresponding constant input as ue. Substituting these equilibrium values into the ODE gives k sine of xe equals ue. Equivalently, sine of xe equals ue divided by k. So the problem of finding equilibrium positions has become the problem of solving this sine equation. This looks simple, but there is an important detail. Inverse sine gives only one principal value, while the sine function itself is periodic. This equation can have repeating solutions or no solutions at all, depending on the value of ue divided by k. To make the equation easier to discuss, we define r equals ue over k. Then the equilibrium equation becomes sine of xe equals r. A natural first step is to apply inverse sine and write xe equals sine inverse of r. This is useful, but it only gives the principal value. In other words, sine inverse r gives one selected value of xe whose sine is r. But the original equation, sine of xe equals r, is asking for all values of xe whose sine is r. Because sine is periodic, there may be more than one solution in a 2 pi period, and the solution pattern repeats. Or, as we'll see, there might be no solution at all. We are solving the equilibrium equation sine of xe equals r, where r equals ue on k. Graphically, this means finding where the sine curve intersects the horizontal line y equals r. First, consider the absolute value of r greater than 1. In this case, the horizontal line lies above the maximum value of sine, or below the minimum value of sine. Since sine only takes values between -1 and 1, there are no intersections. So, if the absolute value of r is greater than 1, the equation sine xe equals r has no solution. For the original ODE, this means there is no equilibrium position for that value of the input. The next case is the absolute value of r equals 1. So r is either 1 or -1. If r equals 1, the horizontal line touches the sine curve at its peaks. If r equals -1, it touches the sine curve at its troughs. In either case, there is one solution per 2 pi period. We can write the repeating solutions as xe equals sine inverse r plus 2 pi n, where n is an integer. The integer n accounts for the repeated copies of the same solution pattern. The next case is r equals 0. Then the equilibrium equation becomes sine xe equals 0. Graphically, we are looking for the x-axis crossings of the sine curve. These occur at integer multiples of pi. So the equilibrium positions are xe equals n pi, where n is an integer. This case is worth separating because the solutions occur every pi, rather than once per 2 pi period. Now consider r between 0 and 1. Here, the horizontal line cuts the sine curve twice in each 2 pi period. One solution is the principal value xe equals sine inverse r. For r between 0 and 1, this lies between 0 and pi on 2. The other solution comes from the symmetry of the sine curve between 0 and pi. The same sine value appears on the other side of the peak, so this solution is xe equals pi minus sine inverse r. To describe all repeating solutions, we add 2 pi n to each one. The full solution set consists of two families, xe equals sine inverse r plus 2 pi n, and xe equals pi minus sine inverse r plus 2 pi n, where n is an integer. Finally, consider r between -1 and 0. Again, the horizontal line cuts the sine curve twice in each 2 pi period. One solution is the principal value xe equals sine inverse r. For r between -1 and 0, this lies between minus pi on 2 and 0. The other solution comes from the symmetry of the sine curve between minus pi and 0. Since sine inverse r is negative, minus sine inverse r is positive. So starting from minus pi and moving forward by that amount gives xe equals minus pi minus sine inverse r. To describe all repeating solutions, we add 2 pi n to each one. The full solution set consists of two families, xe equals sine inverse r plus 2 pi n, and xe equals minus pi minus sine inverse r plus 2 pi n, where n is an integer. The takeaway is that inverse sine gives one useful value, but not the full set of equilibrium positions. For sine, we may need to specify one equilibrium value, restrict xe to a chosen range, or describe the full repeating pattern. The important takeaway is that, for a system with an input, an equilibrium is not just the value xe, it's the pair xe-ue. For our example, the equilibrium condition is k sine xe equals ue. If we choose xe, this equation tells us the constant input ue needed to hold the system there. But we can also go the other way. If we are given ue, then we have to solve k sine xe equals ue to find the possible equilibrium values. As we just saw, that equation may have no solution, or it may have several repeating solutions. Once we choose the equilibrium pair, we can linearize near that pair. For this example, the local linear model contains the coefficient k cos xe, so the chosen equilibrium still matters. The takeaway is, first choose or find the equilibrium pair, then linearize near that specific pair. We are not linearizing the system globally. We are building a local model near one chosen equilibrium pair, and different choices of xe-ue can lead to different local linear ODEs. Let's finish by summarizing the equilibrium finding recipe. First, start with the ODE you want to analyze. Second, set the time derivatives to 0, because at equilibrium the system is not changing. Third, substitute the equilibrium values such as xe and ue. For larger systems, there may be several system variables and several inputs, so all equilibrium values have to satisfy the equation simultaneously. Fourth, solve the algebraic equation that remains. This is similar to finding roots, but these are roots of the equilibrium equation, not characteristic roots. Finally, check which solutions actually exist. As we saw, a nonlinear ODE might have no equilibrium, one equilibrium, several equilibria, or a repeating family of equilibria. This matters because linearization is local. Before we linearize a nonlinear ODE, we need to know which equilibrium point or equilibrium pair we are linearizing around.